Yeah. Yeah. So I think he was having a question of why, what is this part, how this has been corrected, right? This has been corrected. Yeah. Yeah, yeah. So the bias was incorporated. So the difference is, as I was mentioned, uh, same figure actually. So you have, I think the model that has been developed was what y equals to some function of some u and theta, u comma theta, right? U comma theta is the model that is being developed actually. Okay, so this for this, like, I need a correction because the model may show some bias over a period of time. So I need some correction. So I would like to add some error factor here, or we call it as a bias. Bias correction is called. So this bias correction is generally a difference of your error, means the whatever the past error, because currently you don't have any sample, right? When you're predicting in real time, you don't have any sample. It comes only after 6 hours. Only the thing that you have is a past sample. So can I have the error? Let's suppose you're predicting at kth sampling instant. K is the current sampling instant, but I have a past measurement of k minus 6 hours. The past sample is there, past 6 hour sample is there, and minus its prediction at that time. What is the prediction at that time? Okay, at k minus 6 hours. K minus 6 hours. So I have an error of this part. So I add this error to the current time error actually, so that bias can be pull it down actually. So initially it may start with let's suppose this is actual true plant data, and this is what this is a true data, and your sensor is showing, your predictions are showing here, somewhere here. Okay, so as and when you get let's suppose you have this, as and when you get this measurement data, this error is there. So I add the error to the sample, then immediately there will be a shift in my predictions. Okay, then again you can come closer to it. After that, at certain time again there will be a deviation. So then whenever the new sample comes, right, so I'll again add an error to it, then it will again push back to it. Okay, I keep updating this error as and when my measurement comes from the plant. This is coming from the plant at every 6 hours, and these predictions are real-time predictions every time. So I take this error and I update. Whenever the predictions are going bad, I'll update it actually. Okay, and there is a mechanism of when to update also. Sometimes there is no need to continuously. If the predictions are coming close, I no need to correct it, right? So there is a mechanism when to update, when not to update also actually, kind of. Okay. It is kind of a, you can say it is not an auto regress. Auto regress is different. It is error handling. Bias. I'm just adding a bias. The past error I'm handling. Auto regress is you are trying to use the past measurement as a feature. Here it's not a feature. It's just an error actually, and you are estimating the coefficient of that feature actually. In the case of auto regression, in this case it is not actually. Okay. It is just an error, past error, and just adding and keeping it constant till the new measurement comes, and again update error and I keeping it constant till the new measurement. Yes, prediction plus error. Yeah, this error is the past error, because you don't know current error, because you are not getting any sample, right? If you know the current error, why I need a model? Right? I don't know the current error. Actually. I know the past error, so that's why I'm doing it actually. Okay. Yeah. So yeah, I think we will get into the actual phase. This is what kind of a motivation. You can think that whatever till we have come till, it's just a motivation of the next part. What I want to start upon is I think you have seen the development of a soft sensor, right? Predictive model. The most important thing is detecting the abnormalities in the process data. If you're able to detect the abnormalities and clean the data set, that is a major job is done. Your job is done. 90%, 80% job is done. Then the model training, model selection, model parameter fitting. That is a remaining part of it. Okay. So, but as we see, for the case of missing data or the outliers, actually, these regression-based models are use deterministic approach or a crude way of handling the data. Like you use 3 sigma outlier detection, and missing data is you try to impute the missing data values actually. But can we handle it in a more elegant way? Can we do that data pre-processing in a more matured way actually, kind of more better way? So one can do that by formulating your regression problem. Regression is a deterministic problem. Can we formulate in a probabilistic sense. So if you can formulate in a probabilistic sense, you will have more freedom to actually handle missing data case actually and modeling the outliers. You can actually model the outliers. Okay. So what we are doing it whenever there is an outlier detection, let's suppose this is an output variable and you have 10 input variables and there is a outlier is there in the output. So when you want to fit a model, what are you doing? You delete the data points of this one and also corresponding you are deleting the inputs also because you don't want to use this data in your modeling, right? You agree? You're doing a downsampling. Whenever the output is bad, you want to fit a model, you are correspondingly the inputs are also you are eliminating and you're downsampling the data. Got this? We discussed that only starting. We are discussing. In that way, what are we missing? Actually, we are missing the data, the good process data. But when you formulate it in a probabilistic way, you can actually estimate the data points actually. We don't need to remove the data points. We can actually model that this is an outlier. You can try to model this an outlier and no need to remove the input data points. Okay. We no need to remove the input data points. Yeah. Okay. So let's see how we can formulate. I think it's important. I think Professor Bhushan suggested that he has slightly given a touch upon it. We'll get into slowly understanding of how do you formulate a regression problem into a probabilistic sense. Okay, so that's what we want to do in this section. So these all things can be addressed nicely, like when you have a data, like a noisy data. When you have a data with noisy, this blue corresponds to the actual signal and true is the filtered signal actually. Blue is actually noisy signal. It's very fluctuating actually. The true value is around 20, 24 constant, but actually when you are getting a signal from the sensor, it's very fluctuating actually. If I use that variable directly to my sense controller or something, the controller knows that there is something variable keep on changing and the action also keeps on, either it may open the valve, close the valve, open the valve, close the valve and the valve gets off, right? The sensor, the data that you're getting is highly fluctuating. But it's actually the variable is not fluctuating, it's constant. Actually, the sensor malfunctioning, it's called sensor noisy problem, and the missing data, sensor drift, and this process mode changes. So can be elegantly handled when you look into probabilistic way. You can get a good derivations. You can get actually good, what do you say, the deterministic way like handling regression, it's a crude way of handling. So I'll use some board because I could not get enough time to make this, some slides of it actually. I wanted to make slides. I'll just teach in board for some time and later on we'll switch it to the presentation mode, okay. So, yeah. So till now, I think let's suppose you have a data set of y is your variable data point, y12. See, we are all looking at a supervised learning part. I am only looking at a supervised learning and you have an input data set u equals to, so u1, u2. So let's suppose um is the set of m cross 1, n cross m variables. This is a matrix and D corresponds to total data matrix. This is an input data u and this is an output data y. Okay. So now I want to build a model between the input and the output data actually. Okay. So let's suppose I want to build a model of y equals to x plus au plus epsilon is my model that I am choosing it, right? Epsilon is a model. In the case of regression, what did we do? We just went directly saying that this is my linear model and I want to minimize the error. So I took sum of errors I equals to 1 to n error square ei square with respect to theta and I am going to get theta hat. I am going to solve this optimization problem by using any of the solver optimization solver available in the Python or MATLAB. I'll choose this and solve this problem. So we directly solve this problem. Okay. Yeah. But here, did you assign any distribution to it? When you are solving the regression, did you assume that that error follows any distribution? Did we do any distribution in the sense any Gaussian distribution or beta distribution, gamma distribution? What is the distribution that it follows? We are not considering it. It's an error. There is an error in it and we want to minimize the error. Okay, that's what we did it actually. But This error means this error is because the uncertainty in your measurement. Okay, you're saying there's an uncertainty in measurement, you want to reduce that, so this error. So now I am assuming that this error can be follow a Gaussian distribution with a certain mean 0 and variance sigma square. Okay, so I think everybody would have done their statistics, probability and statistics course in 12th or in your BTech first year or second year, like where you know like a random variable. It's a random variable. There's error is uncertainty. Okay, it's uncertainty. It's a random variable. If it's a random variable, it has a distribution. Okay, the simplest distribution to assume is Gaussian distribution because it has two moments. One is mean and one is variance. If I know mean and variance, I can able to characterize this random variable. Okay, I can able to predict the sample of random variable by knowing only the mean and variance. Okay, so I'm assuming that the uncertainty in the measurement, the model is random variable. Okay, fine. So now with this, what happens? If this is random, what about this one? It is a random variable actually. It's a random variable now. Okay, so there is this. I'm assuming that the uncertainty which is entering into your measurement model is a random variable, which is Gaussian distribution, and input is constant. It's a deterministic. There is no constant. It's an input constant, and it's a linear. So output also will be a random variable. So this is also a random variable. Okay. So output is also a random variable. So now I am interested in order to means considering this randomness, I wanted to come up with a how do I estimate my A value, the parameter. Okay. So the simplest way is go regression and solve the problem. Okay, that's the way. But I want to see it in probabilistic way because I have advantages. If I go in this direction, I have advantages. I can solve the problem in a much easier way. So I wanted to go in a different direction. Okay. So see, because since this is a Gaussian distribution, the y it's a linear. Gaussian has a nice properties of linear propagating. Actually, if error is a Gaussian, and if it is a linear distribution, y is also follows a Gaussian. Okay, so if it follows a Gaussian, y follows a Gaussian. Let's suppose this is one sample. I am considering only one sample in the n samples. yi, yeah, and ui. U is corresponding input and y corresponding output. So then yi follows a Gaussian distribution with what is the mean of this one? Gaussian distribution has two moments. We call moments. We have mean and a variance of it actually. So what is the mean of this one? How do you find the mean of this one? Sorry? No, I have equation which is just a random equation. How do you find the mean of it? Sorry? Mean is also same. AU1. So see, this is a random variable. It's a function. Okay, it's a function. It's a random variable. So this can take multiple values. Okay, so if I keep changing if I sample it, I can. These samples can be infinite. I can get infinite samples. Okay, how do I find the mean of the infinite samples? It's a function. It's not data points. If you have a data point, some data points, mean is average of it, right? You assume. If there is a function which is a random and it can generate infinite samples, how do you get the mean of it? There is something called expectation operator. It's an operator. We want to use some operator called expectation. Expectation is like it's operator. It's an operator for these kind of functions actually, where you call expectation. If you have a sample data, the expectation is nothing but 1 by n equals to summation of expectation of x is nothing but 1 by equals summation of xi. I equals to 1 to n. It's a mean. Expectation 1 mean. So if I have infinite samples, then I use something called expected value of yi, and I'll send it as expectation of ui plus expectation of error. It's a linear operator. I use an operators actually because it's a random function. Okay, I want to find the mean of the random function, so I use expectation operator. When I use expectation operator, what about expectation of mean of this one? AU 0? is constant because ui is only one value. It's a constant value. There is no randomness in it. There is no randomness in ui. There is no randomness in a. It's a constant. So I get a ui. What about the expectation of error? Error follows Gaussian distribution with mean 0 and sigma square. What is the expectation of error? Error follows Gaussian distribution with 0 mean and sigma square. Its mean is 0. What is the expectation of error? Is 0. Because its mean is 0, right? The expectation is 0 actually. So I'm going to get a mean of AUI actually. I'm going to get a mean of AUI. Okay. So a similar way one can also derive the variance of it. So the variance means, why you need variance? Because I'm saying I assume some randomness uncertainty. I'm assuming a distribution to it. It's a Gaussian distribution. Because of the Gaussian distribution, yi also becomes a random variable. If it's a random variable, and since it's a Gaussian, this also becomes a Gaussian. It's a linear property. It's a Gaussian. If it's a Gaussian, it has two moments: mean, variance. If I know mean and variance, I can characterize this. I can generate samples actually. I can generate samples independently. Okay. So I found the mean of it. Then I need to find the variance of it. Okay. So what is the variance of it? So variance is nothing but expected value of yi minus mu whole square. Okay. yi minus mu. If I do it, the variance will be the variance of the random variable, the sigma square. Whatever the variance, is coming from here, right? The variance is coming from epsilon. So the variance of y will be the variance of error. Okay, epsilon square. So now yi follows a mean a into mu I and variance sigma square. You agree? Is clear? Okay. The base because epsilon follows Gaussian distribution. Y, because it's getting added to it, there is no randomness here. It's a deterministic value. So output is also a Gaussian distribution. It follows a Gaussian distribution. And so if it's Gaussian, what is the mean and variance? What is the parameters of it? Okay. So the mean is this one and the variance is sigma square is this one. Okay. So like that, how many samples I'm getting? I'm getting n samples. Yi follows a Gaussian distribution with mean if AU y comma sigma square. Like that you are having n samples, each one following a distribution, right? Un comma sigma square. Okay. Sorry? You agree this one? Each one following a distribution. Each measurement is now a random variable following a distribution with mean and a sigma square. Okay. So I'll tell an example of to understand what we are going to do. So you know exit polls, right? Exit polls. Exit polls. Sabko pata hai actually. So what they do in the exit polls? They'll take a small sample. From the small sample, they don't go to all the Nagpur, right? They go into some locations where the different kind of regions are there. They try to locate actually kind of. And they take some samples here, samples here, samples here, samples here. So these are these samples. Okay. Okay. These are different samples. Okay. Coming at it. And each sample is independent. It may be dependent because of biasness actually. So I assume that each sample is independent. Let's suppose I'm taking independent samples without any bias actually. Each sample is independent. Okay. But these samples are all actually coming from some distribution. It's a random distribution. It's, if you can model this sample's behavior. I want to model the behavior because I cannot go entire Nagpur and find out what he has voted or whatever he has voted. I'll only take some samples. Then I'll come back. I'll use the data and try to actually build a model. Okay. Actual means what does this behavior of this samples corresponds to? Okay. So this behavior of the samples corresponds to underlying distribution, Gaussian distribution, or whatever the model that I'm assuming. So if I want to know underlying distribution of it, what are the parameters unknown here? Ui I know, A is the unknown parameter. Okay. So I want to know the A. If I know the A parameter, then I'm constructing a distribution of it actually, okay, which fits this particular data. Okay. Once I construct a distribution of it, then I can generate samples. I can project samples. Okay. I can generate samples and also say that whether a new sample is coming, what is the confidence of this sample? What is the probability of this sample belonging to this distribution? Okay, I can say that. So now I'm going to construct this distribution actually. I'm going to estimate the parameters of the distribution. In the simple regression, you are estimating the parameters of the model, but now we are constructing in the probabilistic sense actually. Is this clear? You have n samples, each following a distribution. Okay, you just listen, you will understand what we are doing at the end. Okay, just carefully digest it. Because if you understand this one, and if you go back, and if somebody wants to learn Bayesian networks, Bayesian neural networks, which is advanced, you can actually take this all fundamentals and go back and understand the actual advanced parts. These are basic fundamental things which I want to touch upon. You can go back and read, understand this part. Okay, so just see. Now you have this data. Means each n samples are there which are coming from each distribution. I assume that the sigma square is known. To simplify, I am assuming that the uncertainty in the random variable is known. Okay, this is known parameter. If this is known parameter, this is unknown. The parameters of the model are unknown. The only parameters which are unknown are parameter A is unknown, input is known, and the output is known. So now I want to estimate. I know output data, I know input data. Now I want to estimate the parameters of A, which are hidden, which are hidden. Okay, how do I do it? Through probabilistic way. Okay, so I think everybody had an idea of joint distribution, joint density function. Huh? So you are not in mindset that sir we started with machine learning and you are going somewhere, right? Okay. So let's hold on. So now you have n samples. I am assuming that sigma square is known, A is unknown, and these all samples are independent. This identically distributed. This is called IID samples. These are each sample is independent to the other sample. They are identically distributed. IID samples. They are called IID samples. They are independent and identically distributed random samples. Okay. So I need this assumption. This very critical assumption which I am making it. In reality, when you go and collect samples of any particular pole or exit pole you want to do, they may not be independent. They may be dependent samples because one can have an influence on other parameters. There can be bias actually. So this is an assumption to actually simplify your problem. Okay, so I'll assume that they are independent and identically distributed random samples. Okay, fine. So now you have this batch of data. Okay, so now I will write from here I'll go and write a joint density function. I have now given n samples, y1 to yn samples, and all these samples follow a distribution of Gaussian distribution with certain parameter A and U and sigma square. Okay, so given this one and these are following this distribution, now I will write a joint density function. What is joint density function of y1 to yn? What is this joint density function after taking this assumption? I am taking this assumption. Product of individual things actually. So it's a simple, right? I simplified the problem actually, kind of. If I don't take independent, identically distributed samples, then I cannot, it's very complex. This is a very complex problem actually. You agree? Since they are independent, I am saying, now I can write this as product of y1, product of y2, product of yn. This f corresponds to the density function. It's not function, it's a density function. It's a Gaussian density function. Fine? So I think everybody knows, I think you would have studied the Gaussian density function is f of some variable y is 1 by square root of 2 pi sigma square into exponential of minus of yi minus mean of it whole square by 2 sigma square, right? This is what f corresponds to, the density function of Gaussian distribution. Okay, so now you have n samples. I have written as a product of individual n density functions. Okay, so now when I further let me go. Now f of y1, right? For this, if I do product of this n times, thanks. Please let me know if you are having any doubt here actually. This is important. You need to understand this this way so that you can try to formulate your problems into this one. So now f corresponds to one Gaussian distribution. F of y corresponds to one particular. So I want to multiply a product of n terms. What do you get when you have a product of n Gaussian distributions? You have exponential here. Sum. So I'll get 1 by square root of 2 pi sigma square whole power n. Agree? This is the product of n into exponential of minus summation of I equals to 1 to n. You get yi minus mean of yi. What is the mean of yi? This is, you get mean, right? When you have a, when you see a Gaussian distribution, you have a actual value minus its mean, subtracting from the mean. So you know what is the mean is nothing but a into ui, okay, whole square by 2 sigma square, okay, exponential of this one. So this is the joint density function, you got it now. This is, you have written a joint density function and this is what you got, okay. So now, if I'll say now actually, okay, this density function means it gives probability, right? It gives what is the probable value of this particular measurement belonging to this density. Okay, so this is the data which I've collected from the particular sample and I want to fit a model to this data. Fit a model to this data, okay. If I want to fit a model to this data, this density function should be, if let's suppose I assume that this data is coming from this density function. I have a model and I'm predicting some samples. I'm saying that these samples are coming from this density function. So then what is the probability should be? Probability of the sample belonging to this density function should be low or high? It should be very high. It should be high because you are saying that these samples are belonging to this density function. So the probability of, or likelihood, we call likelihood of finding this sample belonging to this density function is high. So I wanted to now maximize the joint density function. I want to maximize the joint f of y1 to yn. So I want to maximize the joint density function. So in order to maximize this, what is the parameter that I have in hand? I want to develop a model such that this data fits to that model. So what is the unknown parameter here? Theta, that is A. So I wanted to maximize, this is called a likelihood function, which is called a likelihood function. I wanted to maximize the likelihood function such that for a known parameter, means for a particular value of theta, this data belongs to that particular model. Okay. Okay. So let's suppose if you see here, if I choose an correct value of A, correct value means optimal value of A, such that this data belongs to this density function. What happens to the error? Error becomes 0. If error becomes 0, whatever the density function here, because the exponential of it, it comes close to 1, means density is probability close to 1 actually. So I wanted to find the best value of theta such that the likelihood of y1 to yn seeing this coming from this distribution is maximized actually. I'm trying to maximizing the likelihood function. This is called likelihood. I'm trying to maximize the likelihood function. Is this clear? After that you should not just say that was something actually. Yes. Sorry? Yes. Because I want to fit now. I'm saying that this data is coming from the sample, but I don't know the underlying distribution. I don't know the underlying distribution. That the underlying distribution has a mean and a variance. I don't know what is the mean. Mean is A into U, right? I know U data, but I don't know the mean. I don't know the underlying distribution. I'm trying to fit here actually. Any distribution, you can choose any distribution. I'm just choose Gaussian distribution here. You can choose exponential distribution. You can choose gamma, beta, any distribution. Yeah, I'm completely considering Gaussian everything, everywhere. There is no, you can actually change, you can consider that your error uncertainty is a different beta distribution or gamma distribution or T distribution. You can choose any distribution and construct your model accordingly. Why I'm considering Gaussian is the simplest distribution actually. Means it gives nice, you will see now. Why I'm considering Gaussian, you will see. At the end you are going to come up with a least square problem. Gaussian. Yeah. It is because it is Gaussian because see, you are considering the likelihood of the measurement, right? Measurement. What is the measurement follows? Measurement follows certain distribution. It's a Gaussian distribution. Measurement is coming from the error actually. Means the uncertainty in the measurement is because of the uncertainty present in the error. Okay. The error we are assuming that it's a Gaussian. Then the measurement follows a Gaussian. Then we are saying that the likelihood of the measurement actually. Joint density function. We are considering a joint density function, which is a measurement actually kind of. So that is again a Gaussian. The density function is again a individual Gaussian. So when you write the likelihood function here, joint likelihood function, it is a product of individual density function. What is the individual density follows a Gaussian distribution, right? Got it? So we are going with a Gaussian actually. So why it is coming as a Gaussian? Because it's inherent. When you are trying to write a joint density function, you assume that the measurements are independent. You are going to get independent density functions. Each density function follows a Gaussian distribution. Right? It has its own Gaussian distribution. So that's why you are getting this particular structure. And you are maximizing the joint density function. Actually, it means it's likelihood. Yes, we're calling it as likelihood. It's actually maximizing the joint density function. Okay. Means why you call likelihood means it's the same function you are maximizing. It's not a different function. We are maximizing the joint density function, but in terms we are saying that we are trying to increase the likelihood of seeing this data coming from this distribution. Okay, understand? I think it will take some time to go back actually. Yeah. Any more doubts? Yeah. I think you have some more doubts. Belonging to Rayleigh distribution. Okay. No. You should say, okay, Rayleigh distribution, how the Rayleigh distribution is entering. Where means is the Rayleigh distribution is in the uncertainty? I am now modeling the uncertainty as a Gaussian distribution. If I am modeling uncertainty as a Gaussian distribution, my measurement model is a linear model. Output is also a Gaussian because Gaussian has a linear property. Okay, so it is like this. So y equals to ax plus b plus error, right? There is some uncertainty here. I am assuming this as Gaussian because that is the randomness in it. See, I am measuring a sensor. From a sensor, I am measuring the measurement. So that is coming, keep on fluctuating because there is some uncertainty in it. So I don't know what is the distribution of this uncertainty. I am assuming it as a Gaussian. If I am assuming it as a Gaussian, this is a linear property. Y automatically is a Gaussian. Same thing if you are assuming this as a Rayleigh function, then y follows a Rayleigh distribution and the likelihood is also a Rayleigh function. Yeah. Okay, that's a major key assumption. Gaussian is the simplest because you will see now you are going to get a nice structure actually. Okay. Fine. Till here it is clear. We are maximizing the joint density function with respect to theta. Means we wanted to use known information and unknown information, input and output data to identify the distribution, to identify the hidden parameters theta. So we are trying to maximize this with respect to theta equals to theta hat. Okay. So maximizing the likelihood function, just a function is similar as, or I am trying to maximize theta logarithmic of it. y1 to yn theta. F is exponential function. In this case, f is what? It's an exponential function. Okay. So if I use logarithmic of it, log is monotonous increasing function. Okay. The similar means again the function you don't get a different value, the same value you will get actually. It's an increasing function, but the problem will be much simplified now. I'm using logarithmic of a particular function. So if you see that now, if I go ahead with this maximum of theta, log of this one, what happens? You will get log A log of constant. Let's suppose log of these are all constant. Sigma square is known. Log of constant plus log of exponential of this one. Okay, so you'll get minus of summation of I equals to 1 to n yi minus a into ui square by 2 sigma square. Fine? Yeah, log constant plus this one is, you're getting this one. So then, if this is just a constant, right? If I just use first order optimality, that is a great differentiation with respect to theta, this becomes 0. It doesn't have any value actually. It doesn't shift your optima. This doesn't shift your optima. Okay. Now you have this one. So how does it look? This sigma square is constant again. It is known value. So this looks like where we started. It looks like how? Least squares actually. So maximization of theta, you have log of constant and minus of summation of I equals to 1 to n yi minus a into ui square by 2 sigma square. Okay. So if this is a constant, I'll remove it. I don't want, and it is maximum of negative it is. It is nothing but minimum of I equals to 1 to n. Agree? A into ui square by 2 sigma square. Maximum of a function is nothing but a minimum of negative of that particular function, right? So you'll get a minimum of this particular, and sigma square is constant. Okay, so you are actually solving a least square problem. The same problem you came up with in a different perspective actually, kind of. It's initially you started with the least squares. A regression problem, but now you assume the distribution and you came up with this particular problem. You're solving a least squares. Okay. Why I derived this part is, now we will see that when we come on to Bayesian networks, these all will be useful there actually, kind of. So how you are trying to formulate a joint density function, how are you going to write joint density as independent density functions, take logarithmic of it and maximize the likelihood. When you maximize the likelihood, you are going to get this, this is the objective function you are going to solve. When you solve this problem, you are going to get a theta hat. Okay. Yeah? Is it clear? Maximum likelihood estimation. So you are assuming some density distribution to uncertainty and trying to formulate a maximum likelihood problem where you are trying to maximize the joint density function with respect to theta. Okay. Yeah? Good. Okay, now let's move to something more interesting. I wanted this has to be introduced before getting into the actual something called Bayesian networks or probabilistic graphical models. Okay, so in MSc, this divided by samples actually 1 by n, or it just a sum of square of errors. Some mean square error. Yeah, in mean square error you do it. Divide by n actually. Yeah. But general least square errors. In general least squares, you do you divide by n? You don't divide actually by n. I think when you divide by 1 by 2, you'll get 1 by 2 into general weighted least or least square problem. If you just see a least square problem, sum of square of errors, 1 by 2 into sum of square of errors you get. Or when you see a neural network objective function, 1 by 2 or 1 by n? N. 1 by n you do it actually. Okay. So I think, are we missing something here? You take log square error. It's a square error actually, and it's a weighted. It's kind of a weighted least squares. It's not just a least squares problem. This is a weighted least squares because you have 1 by 2 sigma square dividing. Sigma square is a variance of your measurement variable. Depending upon the measurement, which measurement you are considering, the uncertainty is different. So you are dividing by sigma square actually, kind of, yeah. So I think this is just a sum of square of errors actually. Yeah, it is not a mean square error. It's not a mean square error. Yeah. Okay. So, so I wanted you guys to know how to formulate a joint density function and maximize the joint density function to get least square problem. This is clear, right? Okay. Now let's get into Bayesian networks. So the same problem. Okay, why we need to go? Okay, now you understood that you have a regression problem. You solve it using optimization, generic optimization, forgetting about distribution of it, and you also have a probabilistic version of it. Okay, you assign some distribution to it, uncertainty to it, and you can formulate it. But one thing that is missing here is when you solve both the problems. So are you considering any cause and effect relation between the variables? You are just solving a regression problem. Means you are trying to solve. Let's suppose you have a process or you have a set of inputs u1, u2, u3, and you have output. Okay, so you are just solving a kind of a y equals to function of u1 to. You are fitting a simple model actually. You are trying to, in both the cases, in the probabilistic or deterministic, you are trying to fit a regression model. Okay, then you are trying to fit a model. You are trying to identify the parameter a in both the cases. But are you trying to find any cause and effect relationship between the variables? You are doing one correlation analysis initially to find the initial structure, initial feature selection, but later on you are not incorporating any process information to it actually. Okay, so can we come up with, rather than just fitting a regression model, or rather than fitting a straight function model, can we come up with some sort of flow information adding into the network or adding into the model? Okay, some form of graphical representation of a regression model. This is just a linear, you are fitting linear model, you are fitting the parameters of it, either in the case of regression or in the case of probabilistic. But you can have a graphical representation of a model actually, kind of, where I can find what is affecting what. Fine? Okay, so that drives us to something called probabilistic graphical models. One of the popular probabilistic graphical models, I think, why did it shift it? Oh, this is automatic sensor, it is detection. This is here, it's not coming. Oh, it has come, yeah. So, yeah, now I want to not just fit a model by using input-output data. I wanted to understand the structure also. If there is any structural relation between the variables actually, you can able to come up with some structural relation and fit a model. Okay, I want to use the structural information. Okay, so this is graphical models are popular models where you can get some visual representation of what is happening in the process and then do the regression. Can you come up with regression but using a structural process? Okay. So, so here you can see one example of, let's suppose your output is your lung cancer. Okay, your output is lung cancer. Okay, so and you have set up several input variables. Can I come up with a graphical representation of it? And if I get a graphical representation, then I can get the uncertainty associated with it. Okay, so in the initial case, previous case, when you're doing a regression model, you are assuming that you have uncertainty only in the error. But now I am saying the uncertainty is there in every variable. Each input is uncertain, output is uncertain, all the variables are uncertain actually. There is all randomness in it actually. Okay, kind of. And I wanted to find the uncertainty in each variable kind of. Okay, so Bayesian networks gives a graphical representation of these particular variables. Like let's suppose this example where you have a lung cancer. This generally lung cancer can be caused by two variables. It can be smoking or it can be because of the home conditions actually, or the exposure to the pollution or whatever it is. But that is again connected to socio-economic status part of it actually. Okay, so can you able to reason the uncertainty? Means can you able to predict if this is the output, so which variable is having more probability kind of. So each variable now is a random variable. It has its own distribution assigned with it actually. So can I able to come up with this kind of structure in regression? Suppose I am predicting some particular variable. I have some n variables. So how these n variables are connected to this variable actually, kind of. It is not just how you fit a linear regression model. It is, do you have any certain relationships actually kind of, where you can incorporate some relationships, whether this particular variable is influencing the output variable in this particular manner kind of, okay. Yeah. So here we are considering each variable or inputs and outputs, everything is random. We are relaxing further. Initially we started with regression, there is no randomness or uncertainty, a distribution associated. Then we went into a simple maximum likelihood estimation. We are saying the uncertainty is in the error. Now we are saying that the uncertainty is there in every node of a random variable, okay, every node of a random variable, okay. So, so why do we need Bayesian networks? I think when we start, you'll understand, but before that I'll say that, see here, one assumption we made here, right? When you have n samples, which are sampled from a distribution, and you made assumption of IID, individual independent samples, independent and identically distributed samples. You made this assumption that the data samples that are coming are independent identical distribution. When you made this assumption, you're able to write down this distribution. Let's suppose I don't make assumption of, I don't know how these variables are related. Are they independent or are they dependent? On what way they are dependent? I have no idea. If I have no idea, can I write a density function? It's complex. You can't write it actually. You can't write it. If let's suppose you have two variables, it's fine. Okay, if you have 1,000 variables actually, how do you write a joint density function? You can't write it. So better you use some kind of relation. If you can find some kind of relation between the variables, saying that y1 depends on only y2, yn depends on only y1, some kind of relationships kind of. If you can able to get it, then you can break down a joint density function into a individual density functions by knowing the relationship between the variables. Okay, so that can be obtained through Bayesian networks. If I can get a network structure, okay, so you can see here actually, in the case of here lung cancer is directly depending on these two particular variables. And smoking is not depending on this one. And this particular variable depends on this one, right? So if I, let's suppose these are the 5 variables are being given and you have to write a joint density function. Now it's easy, right? You agree? So you have to write a joint density function of these variables. So how do you write? See, we are going slowly from a regression. We are solving at the end you see that you are solving a regression problem, but multiple regression problems are solving, not one regression problem. You started with a simple regression, likelihood, and then you are going to some bit complex case. Let's suppose you have variable A, variable B, variable C, variable D. A corresponds to lung cancer, okay, this is cancer, and B corresponds to smoking, and C corresponds to asbestos, and D corresponds to social status, okay. So now I tell you guys to write a joint density function of it, A, B, C, D. Can you look at the figure and say which one is dependent on which one? You know conditional independence, right? Conditional independence, conditional dependence. F of, let's suppose, start from lung cancer. You start from here. Okay, you have a structure here. Okay, so lung cancer is depending only on asbestos and smoking. Right? So I say that what is lung cancer here? A given this particular information, I can able to predict this information, right? I don't need this information. So this variable depends only on these variables. So A conditioned on B and C. Then go to this part. This variable is depending only on okay. Yeah, here they have used, right, actually. Wait. Yeah, that's good. So let's suppose, so use C, A, S, E. Okay, I wanted to write a joint density function between C, A, S, E. How do you write the joint density? Now look at the figure and start from the down. Or you can start from the top. Social economic, okay, E is there. Whether E is depending on any other variable? No. So E is depending on its own E, f of E. I'll write it f of E. It's an independent variable. It's an independent, you'll get it. Now next come to S. S is independent. Okay. F of S is independent. What about A? A depends on it. It's a conditional dependence. A given E. It depends on E, conditionally depending on E, it's depending on E. Next, f of c depends on A and S, right? So you're able to easily structure it. What if you have n variables and you know the relation between the variables actually? So you can easily write down this joint density function. If this, let's suppose this structure is not given to you. How do you come up with this density function? If I want to formulate a likelihood problem kind of thing, I need to write a joint density function. So I can't write a joint density function in a simpler way. So I can use a network structure here, which can use cause and effect relationship between the variables, and I can easily break down a higher dimensional system into a very independent dimensional system. It is one advantage of it. Okay. The other advantage is like you're introducing some cause and effect relationship between the variables actually. Okay. So that is, and each node or each variable in the network structure is random now. Now we are introducing bringing randomness more into it. Initially we said that the input or the model, the x value is not random, it is constant, but in general this also can be a randomness. The input variable affecting the process can also be a random variable. Okay, so you can bringing that one, and the major advantage of it is, like you will see that I think I'll once you write the joint density function of a Bayesian network, simple Bayesian network, you can easily write a joint density function for a missing data, outliers actually kind of. So you can easily address inherently the noise characteristics, everything can be addressed inherently without adding any additional layers to it actually. Okay, yeah. Any doubts? You're able to process? Okay, so shall we go? Okay, so this is fine, and yeah, I think we discussed the advantages is done. So yeah, one basic thing is in the regression part, you are not introducing any structural relation, cause and effect relation between them. You are just having input and output. Initially, you found the correlation analysis and then fitting the model. Okay, but some kind of flow information from the process or process flow diagram, if you are having, you can actually bringing that information into the network structure. Okay, you can come up into the network structure. Okay, so that is one major advantage of the Bayesian networks part. So let's. I think this is an outlier. Yeah, I think this figure has topped up actually kind of. Okay. So there are three cases. I think regression was simple, likelihood was bit by understanding the density. But Bayesian network it's not so straightforward. You have multiple things actually. The first thing that you need to in the Bayesian network based model, if you want to develop a Bayesian network based supervised learning model or a predictive model, the first thing that you need to know is, let's suppose you have inputs and outputs. What is the first thing that you need to construct? Structure. You need to find a relation between the variables. What is the relation between the variables? How do you get the structure? So that's called structure learning. The first part is the structure development. That is a challenging part here actually. So that structure development can be done in two ways. One way is, let's suppose you have a process flow diagram is there. You are in a particular industry where you know how each input is affecting each output variables actually kind of in which direction or what is the flow of the direction. You can use that structural information in a network. Okay, that is one way. The other way is, let's suppose you don't have any structural information, you just have a process data. You have input output data. I don't have any structural information. Can I find a structural error with the data part? Okay, that is the data driven completely. One is core process knowledge based approach by topology and correlation analysis. The other thing is completely score based analysis, means it does an iterative optimization based approach where it tries to find the structure and tries to maximize the score of it. If you're getting a right structure, the score is this much. If you're getting a wrong structure, the score is lesser kind of. Okay, so you're trying to identify the structure. Okay, so now once you identify the structure of the network, you know the network structure is there, then because I want to come up with a supervised model, I want to predict an output with respect to input. So I need to do a parameter learning. I need to learn the parameters of the network structure also. Okay, like how do you do neural network? You have a neural network, right? Input output actually. You have weights and biases. So here also we have some weights and biases where you need to train it actually. So you know how to do the prediction. Once you do the parameter learning, the third part is the inference. Inference is predictions. At one particular variable you want to do the prediction. So there are three layers in the case of Bayesian networks when you want to construct. First is learn the structure development. It can be data driven or from process knowledge available from the flowchart information or from the visual, whatever it is. Next thing is learning, then inferencing, predictions actually. Okay, so we'll touch upon some basic. There are multiple methods are available actually to do these cases. I will go with the Bayes theorem based approach. Okay, Bayesian approach. Okay, fine. Any doubts here? Are you able to get it? Trying to get it. Okay, ठीक है. Fine. I think this has been discussed. Yeah, let's suppose this. We'll start with the basic simple structure, how to construct a structure of or what are the structure represents here. Let's suppose you have three variables x, y, z here actually. So x is affecting z and z is affecting y. Okay. So z is called y is called the child, z is called the parent, and x is called the ancestor of it actually. Okay, so this the one which is getting least affected is the child. Okay, the one which is getting the one which is getting affected is the parent, and we have an ancestor part of it actually. Okay, and each variable, each node is a random variable here. It's not a neural network. When neural network, you have a nodes which are not random, which are deterministic, which are static. Which are neurons actually. Okay, which are static. But here each is a random variable actually. Each can be considered as one input, which is random, which is having distribution, its own distribution. Okay, and this nodes corresponds to the random variables, and the edges corresponds to the direction which is affecting. This direction is having some meaningful actually. It's a meaningful information. Okay, so how this variable is getting affected with this one. So because each process, it's not a neural network. When you look at a neural network, it has a fixed structure of inputs, and you have multiple layers, and you go to your output. But here, each process it has its own neural network, its own Bayesian network structure, because variables influence other variables in a different way actually. So each has its own structures. Okay, fine. So and these are directed acyclic graphs. Means they are direct. Means you have a directions here. Okay, that is important when you want to construct a network structure. If it is there are undirected graphs and there are directed graphs. Directed graphs indicates the flow of information is passing into it actually. Okay, which are Bayesian networks, and the undirected graphs are called Markov models, or I think undirected is some Markov models actually, kind of, yeah, hidden Markov models. Yeah. So and these are acyclic in the sense there is no cyclic nature in it actually. Okay. Okay, it's in one direction, forward direction. If you have a cyclic nature, then you cannot solve through Bayesian networks actually. So you need to do some additional things. Okay, we don't get into that part. So it is a cyclic, it is an acyclic nature. You can see in any structure it is in the forward direction or in acyclic nature. Okay. Yeah. And these are fully connected graphs, and let us go to the next part. Okay, so these are different ways of means when you construct one your process, you get into this different layers of it. So here you can see that given, let's suppose this is x is actually indirectly affecting y, but if I know z information, let's suppose I know what is z and I know the information of z, so then do I require x information? X is not required. X is already have inherently affecting z, so z has the information of x actually. Okay, so it's a way of indirect causal effect actually. I think it's in a forward direction, it's in a backward direction, and here you can cause, this is called a common cause and a common effect variable, where z is affecting both x and y variables. So let's suppose look at the independency here. If z is observed, let's suppose if I know the z, if I measure the z value, or how do you put it actually? Okay. Sorry. Yeah. I wanted to get into that part actually, kind of. I wanted to touch upon, like, I'm just thinking. Let's suppose for the common cause, like where z is affecting both x and y, and I wanted to study the behavior of whether y and x are independent or dependent actually. Okay, so in the case when I know the z information, if I know the z information, anyhow the x and y are independent only actually, right? No, I think I wanted to say something actually here it is. So I think let's get to this the next. I think it is more clear in the next few slides. So these common cause and common effect are having some important significance when you're constructing a network or writing a joint density function. When you're writing a joint density function, these are important actually. Okay. So I think we'll get into the next slides, then it'll be more clear. So these are different ways of network connections. Let's take one simple example of it's a system. It's a simple flow system. You have a flow. Let's suppose you have a pipeline, okay, which is coming with a hot stream of fluid. Actually, in chemical industry or any industry, you can see there is a pipeline which is coming with a hot fluid stream. Then it goes into multiple process. Like you split the SPL correspond to splitter. You are trying to split the process actually, the flow into two directions. One is 2 and 3. And that goes into this valve, and again it comes back to here. And the second goes into heat exchanger. Means it's a hot water. It's getting into heat exchanger where you want to exchange the heat liquid and get into both mixing and doing it. It's a simple process, very simple linear process. So I wanted to represent this in terms of Bayesian networks because I have a flow diagram, right? Nice flow structure is there. Okay, so I wanted to, let's suppose in my real plant, I'm interested in variable 4. I don't have any sensor here, 4. I don't have any hardware sensor, but I have a sensor here. I have a sensor 5, 3, 1, 2, all sensors are available. I don't have a sensor at this position. I want to come up with some predictive model which can predict variable 4 information. What is the flow information which is coming out from the heat exchanger? Okay, the fluid which is coming out from the heat exchanger, what is the either flow information or what is the value of it? I wanted to predict it. Okay, so the simplest thing is if you don't have any idea of a structure, what is the best way? Let's suppose I have not given you structure, okay, but I want to construct a Bayesian networks. I want to construct a probabilistic graphical model, but I don't have any structural idea. Okay, I don't want to use any structure. So what is the simplest way? This has gone. Okay, I'm rotating in a cloud. Awesome. Okay, good. Okay, so let's suppose you are not being given any structure to you. Only the thing that you are given is y1, y2, y3, y5, y6 are the inputs and y4 is the output. Okay, so I want to construct a between input and output Bayesian network model. So how do you construct? You can use correlation matrix actually. Find the correlation matrix and say that the simplest structure is actually two-layer structure. It's called two-layer structure. So saying that all the variables are affecting the output same manner. There is no dependent among the variables. All are affecting the same, like regression. In the regression, you are saying that all variables are affecting the output in the same manner. What is the difference between the regression and here? I'm not adding any relation here. I'm saying there are four inputs are affecting output in the same manner. The difference, the advantage that you're getting is each input is now a random variable. In the case of regression, you are not assuming that actually. It's a deterministic variable. Here you are considering that as a randomness actually. You can have a mean and a variance of individual variable, uncertainty associated with it. Okay, and can come up with this prediction model, Wi-Fi. Okay, but I think as you go, you'll get more advantages of it, you'll see that. This clearly is a simple structure. If it doesn't have any information of the process diagram, you have a data and you want to construct a network structure without using any structure-based learning, anything. I want to come up with some simple Bayesian network structure is two-layer structure. I can just come up with a two-layer structure saying that all inputs are affecting output and train the model. Okay, we'll get into that part. The other way is, let's suppose I have this process flow diagram. This is an industry process flow diagram, and I'm interested in like predicting some quality variable coming out from here, output. Okay, and you have several input variables which are I did already correlation analysis, and these are the features. These are the best features. I selected these 7 variables as best input features after doing correlation analysis, and this is the output I want to predict. But I have some structure. Okay, so the output is getting affected. The first is getting affected with the input 1. Okay, and you also have the input 2 which is getting affected with this output actually, and some other variables. So I can use correlation analysis and topology and come up with certain network structure of it. Okay, I'm using the topology information, how it is, and I'm also using the correlation between the variables, okay, which is the input and output, which variables are correlated higher. Actually, I'm keeping them as the top choice, the one which are highly affected. The second layer corresponds to the less affected variables and based on the significance of the network structure. So this is one way of topological information, correlation analysis I'm using. There are other approaches where you use complete data. You just throw the data to it. It automatically identifies the structure actually, kind of by based on the score-based learning. So I'm not getting into it. I can share you some material if you guys want to look into it. Okay. So one can come up with this structure of this nature. Okay. Yeah. So when you know this structure, so what advantages that you get? Let's suppose I want to predict y8. Y8 is my quality variable which I want to predict, and I got this structure. So can I further simplify it? You have a network structure now. I want to predict yi, and these are all the input variables. So can I further simplify the structure? Yeah, I can actually consider that, okay, why? Because these are the input variables based on the structure. These are the input variables are highly affecting my output variable, and this information is already present in this one actually. So I can come up with a reduced network structure actually. Okay. So reduced network structure, which is called as a blank. I can use something called Markov blanket. They're called Markov blanket, where you consider you have a target variable is this one. You are interested in target variable A, then you look at around the surrounding variables. You look at their parents, their child actually, and their, what is this called? Parents are there, childs are there, and I think these are something. Co-parents of the target node actually. Co-parents of the target node. Yeah, these are called co-parents of the target node. Yeah. So you can look into this surrounding variables and you can actually reduce the network structure. Let's suppose this problem is like a sensor network design. I don't know, anybody has done sensor network design here? Any PhD students? Okay. Okay. So what is your you're doing your PhD? Wireless sensor network. So you can actually, let's suppose you wanted to keep sensors actually, okay, multiple sensors. Like let's suppose you have a jet engine, okay. There you use sensors at multiple locations to measure the temperature of the turbine temperature, inlet temperature of the fluid. So how many sensors you want to use and where to place these sensors is a critical question actually. So if I know the network structure kind of these variables, and I can reduce the sensors actually kind of. I can only say that if I know this information, I no need to put this variable around this particular location, only this particular variables around I need sensors because that has a good amount of information, and remaining I don't need to put any sensors. Like, okay, yeah. So you can reduce the dimension. One way you're doing a feature extraction. Okay, feature extraction, again you did a correlation analysis, you came up with this network structure, again you're doing a feature extraction, you're only considering the variables which are significant. Okay, so the Markov blanket helps in this, like here in the case of network flow diagram. The same thing, if you just go back to this example, this one, if I now, let's suppose I have a network structure, now I'll come up with a diagram of it. I have a network structure and this is what the flow diagram looks like. I have y6 is my output variable, y6 is depending on y4 and y5 and which are indirectly depending on y2, y3 and y1. y1 is the input stream and it is going in this way. Okay, let's suppose my target variable is y4. If my target variable is y4, then I look into its parent, child and its co-parent actually. Only this information is sufficient for me to build a model. I don't need all the sensor information all this at every time because the information is already getting that part. Or I can forget about sensor information, I can only build a model by writing a joint density between these variables. Initially when you're building a regression model, you're writing a joint density of all the variables, right? I can only now write a joint density between these variables and identify the parameters of this network. I'm done. Okay, so I can come up with a reduced network, reduced models actually kind of, okay. Is this clear till now? I think you should try. Actually, we tried that. I think you may sometimes depending on theta. Entire theta. Yeah. Entire all the networks actually kind of. So maybe that's a good question actually. So when you try to come up with a uh, reduced network, let's suppose if I come up with a reduced network, the number of parameters are reduced now. So we haven't come up with the models actually. Now you are going to come up with a you are going to fit a model between here. You are going to fit a model between here. Each individual models you are going to fit, not one model. In the case of regression, you are going to fit a global model. You are going to fit a local models here. For each relation, you have one model actually. Okay. So one way is when you are reducing this structure, you are reducing the number of parameters. Okay, and the data information available is also is reducing. So you may get a better result, or but preferably like you'll get a, because if the information is there available in this Y2 Wi-Fi, you will get a good model with a lesser number of parameters actually. Yeah, with the lesser number of parameters, a good estimate. Yeah, that's. No, yeah, we are going to get only one model. We are going to get only one model, but we are going to use local models actually. Okay, so we are going to use one relation between y6, y5. We are going to use y6, y4, y5. Some relation you are going to use. Okay, so we'll get into that part. How do you do that? First, understand the structure. This part is clear, and the importance of this is clear, right? So now we'll write joint density function. Okay, so if you write a joint density function, so let's suppose for this variable, how do you write a joint density function for this system itself? So let's write a joint density function for y4. If I want to write a joint density, or y6, okay. So you have a variables y1, y2. Each variable is random variable, which is sampling from a distribution. Okay, we'll assume that each is random variable, and I'm relaxing the assumption of independence. Now variable that initially I kept IID sample, independent identically distributed. There are no independent identically distributed samples. So you have y1, y2, y3, y4, y5 and y6. Okay, I wanted to, because they are random, I wanted to use Bayesian network and solve the problem. Okay, they are all random variables. I want to write a joint density function of y1, y2, y3, y4, y5, y6. How to write a joint density function here? I want to break it down. Each is a random variable. Let's suppose we are not assigned any distribution to it. Each is a random variable, and I want to write a joint density function to it. Let's start from base, top or bottom. You can choose anything actually. Let's start from y6. So y6, if you choose, y6 is depending on only on y4 and y5. So I can break it down as f of y6 is a conditional. These are called conditional density functions. So given the information of y5, y4, I can predict y6. It is like that. Okay, I can predict y6. It's a conditional density function. So y6 is conditioned on y4 and y5. Then you go to y5. y5 is conditioned only on y3 because it's directly depending on y3 actually. So it's y3. Now if you go to y3, y3 is conditioned on y1. Okay. And y1 is independent, okay, and then you have y2 which is conditioned on y1, okay. Here I think that V structure, that we have seen the V, right, actually, this part, we have seen common cause, this is a common cause actually. So we'll get back to it, whether they are independent or dependent or, okay. So let's suppose if y1 information is given, y2 is independent of y3. You agree? If I know this information y1, then y2 depends only on y1. Because this is causing this one, right? y1 is causing this one actually. So if I know y1, then y2 is independent of y3. The same way, if I know y1, y3 is independent of y2. That's fine, right? Agree? So that's a common cause relation. So and then you have y4 4 f of y4 given y2 and y6. Now this is, that is common cause, this is common effect actually. Okay. Now y4 given, y2 is over. Now you have y6 actually. Okay. So y6 you already given y4 and y5. Yeah. Yeah, y6 is depending on both the variables y4 and y5. Fine, is this correct? You agree? Yeah, you mentioned now you are able to come up with you have a network structure, you have written joint density function and broken down the joint density function into individual density functions. If you doesn't have this structure, you can't know, you don't know what is the dependence. You should make assumption that they are independent. And only that, then only you can solve, or else you can't solve the relation between the variables. Okay. So the Bayesian network helps in writing a joint density. One advantage is writing a very easy form of joint density function. Fine? Yeah. Now the next question comes, okay, we have now written a joint density function. Now we'll assign, what did we do when we do maximum likelihood estimation? When you return the joint density function, we assign each density function follows some distribution, right? We assign f of y6, y5, y4 follows one distribution, and similarly we are going to assign some distribution between the variables actually. y6 depending on y5 and y4 it follows certain distribution, and the y5 distribution follows a distribution kind of. Okay. There's no idea assumption. I didn't make any idea assumption. Yeah, joint distribution from the joint distribution we made is a product by using the network structure. We didn't make any IID distribution actually. Okay, so I think we may make IID in the samples. Measurement samples, each measurement sample is independent of its own because the uncertainty is present. But each variable, they are not independent now. Variables are not independent. I didn't make any assumption that y6 is independent of y1. I didn't make. By looking at the structure, I have written. I got to know that y1 is independent of all the variables. y6 and y3. y6, yes, yeah. They are dependent, but if I know this y5, but they are conditionally dependent. I mean, yeah, they are dependent on y6 is dependent on y3, provided let's suppose if y5 information is known to me, then this information is present here. So it only directly depends on this one, not on this one. Direct dependence I'm looking. Direct dependence on this one actually. Yes. That's why I've written y6 depends only on y4, y5. Direct dependence is this one actually. So that gives an advantage actually. If this information is already coming here, why I need to again incorporate this variable? I don't need to. Got it? Okay. So yeah, once you do that, you can come up with a joint density function. So the next task is I'm going to assign what does this joint density function looks like. If I know this joint density function, what is it, then the problem is solved actually, right? I can just maximize the density function with respect to theta, unknown parameters. So what does this density function looks like? So each density function, now I split it, in the previous regression case, each density function was Gaussian. Because the samples are independent, each sample was Gaussian distribution and we solve the problem. But here, let's see what we get here actually, kind of. So we do the similar assumption as a Gaussian distribution and solve the problem. You want to stop here or you have 5 minutes? Stop? Done? Some are actually exhausted. Okay. So yeah, I think this is the way you write the major advantage of Bayesian network is writing the density functions, the joint density functions. Before that, you will not be able to write a density function like this, where you have n variables which are which are having certain relationships. You cannot write a joint density function together actually. So Bayesian networks gives a nice structure of writing a joint density function actually, right? Okay. I think one thing that we can stop at of it actually. Yeah, I think we can discuss this part later in the afternoon. I think it will take some time, maybe half an hour. Yeah. We'll stop here. Now I think we are at joint density function. Okay, we'll see now how we construct and estimate. There is a lot to go now. We started with the parameter structure learning, structure identification, structure learning. We came up with some structure. Okay, and then we are writing a joint density function. Now we assign a distribution to it. Then comes parameter learning. Then comes prediction. Okay, there are two more steps are there actually. Okay, so we'll do that, how it is. Okay. I think we can stop now. I think maybe after lunch we can meet. Yeah, 2:15 around. Yeah, thanks. Yeah. Yeah, if you have any doubts, you can ask. We have 5 minutes actually. Any